Welcome to block 2. I've said nothing before this moment. Okay, now we're going to turn in our assignment here. We're going to turn in our submission form. So this is in a bizarre place. So we're going to find this. I'm in mypltw.org. Am I still sharing? Yeah. In mypltw.org, I'm going to go to professional development. Professional development. And it's going to take a minute to load. And I'm going to find, you're going to see all these. Hopefully you have less of these than I do. But you're going to find 22, 23 digital electronics. And you're going to say resume track. And on the right side, you're going to see a digital electronics. You can click that. And you see all your blocks here. And at its base, you will not see my files here. You have to, it's annoying. You have to click this instructions. It's going to download this thing. Fine. Close it. Who cares? And once you do that, you will see my files show up over here. You click my files. And then there's a little file upload right here. And then you will browse and find your Word doc. Okay. You just hit submit. You'll see it in here. Boom. Now, as soon as you submit it, it will say in progress. Okay. That means I haven't graded it yet. Okay. Once I grade it, you'll see one of two things. You will see it either say complete, which is good. That means all good. No, nothing needed. We're great. Or you'll see revision required, which means there's something in there that wasn't quite right. And if you do see revision required, you'll see like your file, and then you'll see I added a file after it where I say, this is what's up. Something's not right. Here's what you need to fix. And then you can resubmit. Okay.
Hey, Mike.
Yeah.
Real quick, you said when you upload a file, it says in progress. It says in review.
In review.
Upload, and
thanks.
It says in progress before you do anything.
Okay. So in review means you turned it in and I haven't graded it. Thank you. Okay. Any questions on turning in block 1? And again, I'd be looking for that, like to stay on track, probably by tomorrow morning before our third session starts. That should probably be turned in. Okay. All righty. So your kids, we're kind of, like I said, we're kind of weird and out of order right now, but your kids start with 111, which is a safety quiz. Now you'll find there is one in the curriculum. Here it is. And they have you take it just so you know you've looked at it. But I would highly recommend that you tailor a safety quiz to whatever makes sense in your classroom. Whatever your school's procedures are, whatever your lab looks like, think about what's actually important for your kids to know from a safety perspective, and tailor your quiz to that. There is some liability to it in terms of, like, you have this document that says at some point this kid knew that they weren't supposed to lick a soldering iron. You know, right here they knew. So, you know, it's not, you know, necessarily hugely legally binding or anything, but at least it's some evidence that you as a teacher took some time to make sure that this kid knew how to operate safely. In every safety quiz I've ever seen, there's always like a dumb question about like classes of fire extinguisher. That is an irrelevant question, because at no point have I ever seen a fire and been like, which class of fire extinguisher should I use? And I look over and I have 4 of them sitting in front of me. Here's a class A and a class. It's impractical, right? That's never happened, right? I grab the one, which is ABC class, and I push the fire, right? That's what I would do. So my point is, like, I would definitely tailor that to whatever makes sense for your classroom. Thankfully, DE is not a particularly dangerous course. The voltages that we deal with are pretty low. The currents we deal with are pretty low. Soldering irons are hot. That's probably the most dangerous thing we deal with. Soldering irons are pretty darn hot, so we can get some burns and things like that. And the leads on IC chips are pretty pointy. And so not infrequently, you'll have a kid like poke their finger with one of those leads and get a little blood. But that's about the long and short of it. So anyway, Moral of the story on that, make it your own. Don't necessarily use this one. Do whatever makes sense. I have had to, I really like, some teachers will put in like what are the rules for, like, if there's a sub, what am I allowed to do if there's a sub in the classroom? Am I allowed, if I come in after school, and there's a different teacher or club, like what do those rules look like? That might be a good thing to put on a safety quiz. So, okay. So that's 111. 112, you guys did it. That's the discovery activity. Let's just see what happens. Okay. So now when they come back to class after they've done 112, this is the first, here's some content. Okay. Here's some actual, let's talk about electricity. And so for that, there is a super secret PowerPoint. Okay. This is a PowerPoint that the kids aren't supposed to see ahead of time because it's a discovery activity. We don't want them looking ahead on this. We want them to just mess around. So the 112 PowerPoint is hidden from students. So if it's hidden from students, you can think about this. You don't have to answer this aloud. But if it's hidden from students, where am I going to find it? I'm going to find it in the teacher guide, the teacher version of this course. Okay. So right now I'm in the student version. It says digital electronics. So I'm going to go back to the library here and I'm going to find the teacher guide, digital electronics teacher guide. That's where I'm going to find this super secret PowerPoint. Okay. And so the teacher guide is like a little hard to navigate. I think it's like intuitively, I don't find things where I expect to find them. And so there's a bunch of good stuff in here, but I'm going to scroll till I see the unit 1 stuff here. Here's my unit 1 stuff. And so if I click on 1.1, okay, they give me a bunch of teacher notes. So this is nice because it gives you a real quick, like if you're like, all right, I'm doing 112 next week, here's a nice little quick paragraph about like, what's the point? What's the general idea? So you've got those, which is nice. So they have all the teacher notes, okay, on lesson 1.1 stuff. Okay. Then if I click the next down here, teacher resources, I can also find it on the left side. Teacher resources. Okay. Here's a bunch of stuff. This is all stuff kids won't have access to by default. It's that's all this is. Okay. The test answer key. Here's that 112 hidden presentation we're about to go through. That's where that is. You'll also find these are nice. They just started doing these a couple of years ago. They're like some worksheets to go along with these activities. So if you're like a paper pencil kind of a person and you want to do that in your classroom, you could like make copies of these worksheets and kids could answer on the worksheet. If you'd like to do that, that might be it's a nice, kind of combination there. So this is the PowerPoint we're going to go through. I'm going to be 100% honest with you. Hello. That was weird. I don't think you should go through this entire PowerPoint with them at this point. It is a monster. It's way too big, way too big. So I'm going to show you like right now, I'm going to take you through what I would go through with my class. And my computer is mad at me today. I don't know what the issue is. It is not happy with Pappy. What is going on? There we go. Okay. So, if I go through this, you will see this is the picture that they saw that you saw in 112. Okay. And there's some questions, some leading questions. Hey, with the circuit active? So kids might have been like, well, what does that mean? I don't know. What does it mean to have the circuit active? Well, I guess that means that the light lit up, right? So the light lit up, and if I flip the LED the other way, the light doesn't light up. And what does that tell you about LEDs? That tells you they only work in one direction. They have a way. They have, we call it a polarity. Okay. They have a polarity. They only work one way. And in the schematic, we kind of see that, right? There's like a triangle on one side. There's a bar on the other. There's a way that they go. The resistor What does the resistor do? This is the point where I can usually point to somebody in class and say, hey, remember when this guy blew up the LED, right? It stopped working and everyone, why? Because he didn't put the resistor in there. Okay, well, what do you think the resistor does then? Well, the resistor, somebody might say, hey, it stops the LED from blowing up. Yeah, that's what it does. Resistor resists, it limits current. Okay, so it protects the LED by limiting the current. LEDs by default will basically accept whatever you put into them. So if you don't limit current with a resistor, you probably burn it out. It'll work very briefly, and then it will burn out. They ask you to measure with a multimeter, and they say everyone read slightly different values. Well, they might not. Partially because of multimeter stuff, because of tolerance, the resistors or the power supplies might give different voltages. So it should be close, but you might see it off by millivolts or whatever. Okay. If you switch the positive and negative leads, we're driving, kids will be like, yeah, there was a negative sign, but it was the same number. Yes, exactly. You get it. Doesn't change the value. It's just the orientation. No big deal. Okay. Now this, if you have the meter that came with your kit, it is not an auto ranging meter. So that means you have to select the range that you're reading. And basically it's a trade-off between precision and what it can read. So on this type of meter here, if I'm on the 600 volt range, I can read a huge amount of voltage. That's great, but I don't have a very precise reading. It might say 5, and you're like, okay, 5 volts, I guess. But if you start to get these smaller ranges here, you get a more precise reading. So maybe it was actually like 4.61, right? But up here at 600, you wouldn't notice that. As you get down to these lower ranges, you get more and more and more precision. Okay. Now, if you have a fancy meter like this one, okay, they are auto ranging, which means they will kind of look at what voltage you're putting in and kind of dial down that range until it's as precise as it can be. You see that here. Okay. So voltage. All right. Now, voltage, they talk about capacitors here just to like explain voltage. I don't love it. I skip these two when I teach to my kids. We'll talk about capacitors more later, but now's not the right time, I think, to talk about capacitors. Okay. They bring in the equation here, which we'll never touch again. This is like a physics connection, but they do not need to know what joules are, coulombs. They don't need to know that volts are 1 joule per coulomb. Like, we don't do any of that. So this is, a spot for maybe physics connections. Again, if you're teaching this to seniors and they've all taken physics, it might be worth bringing this in, but it's not something that we need for this curriculum or this level. Okay. Now, this though is kind of important. Now, voltage, we talk about voltage as like a differential, right? A potential difference. Now, some folks will call voltage a force, and physics teachers will freak out because it's not a force as it is typically defined. But as we talk about like analogy and metaphor and trying to understand electricity, it's oftentimes easiest to think of it as a force. Okay, but it's like a potential difference. So to that end, when they have you measure a wire, you're going to have effectively the same amount of voltage potential on this side of the wire as is this side of the wire. So there shouldn't be any difference between these 2 points, or at least nothing, that should be negligible. So when I put my meter there, I should see 0 volts because there's no difference between those 2 points. That doesn't mean there isn't voltage there. It just means there's no difference between those points. Now, if I measure on either side of the resistor, though, there is a voltage difference there. So I should see something on my meter. And that's kind of a difficult concept for kids to understand, is the potential difference in voltage between those two spots. Okay. Now we're going to get this water analogy. Now, Project Lead the Way spent some money, and they did some interviews, and they went to like professors at electrical engineering professors at various universities. And they said, we understand that there's a problem with water as a metaphor for electricity because, it's not a perfect model. And they said, what is the right way? We want to do it the right way. And basically unanimously, the professors were like, no, we use water that's what we use. We use water to describe electricity. And so like, okay, all right. So I guess we stick with water as a model for understanding. Even though, again, that water and electricity move differently, there are different realities with them, but it is just a good way. People see water, they roughly understand how water moves. And so it's a really great intro into how do we understand what electricity does. Okay. So here we have two buckets. This one has more water in it. This one has less water in it. So if you ask kids what's going to happen, for the most part, they're going to say that this water is going to try and go over there. And that's what voltage really is, right? It's a potential. Like this wants to equalize. It wants to get over there. And that's really what voltage is. I often refer to it in my class as, a force or a push or a pressure, which those words aren't technically correct. And I do mention that, right? But in terms of understanding, at least at this level, I think it's okay to visualize it in that way. Right. If my kids go on to be electrical engineers, they're going to dive in, or physicists, they're going to dive into what these things really mean. But at this level, I think it's okay to kind of simplify it to that level. So this potential difference, that's my voltage, my push, my pressure, right? And then my flow, the amount of water or electricity or whatever, that's my current. Right? How much is moving through here at any given moment? That's my current. Okay. And then they put a little valve in here and they say, okay, so that's my opposition. That's my resistance. That's the resistance to flow. So there's three things going on here. We've got my voltage, my current, and my resistance. Voltage, current, and resistance. And those three quantities are really important, and they're really connected, and they have a really beautiful relationship, which we'll talk about here in a little bit. Okay. But that's what we're kind of trying to see here. And I think we can, let me talk through two more slides. So, they show you a block diagram here for a flashlight and a schematic, and it's worth a couple of sentences of saying it's annoying to have to learn schematic symbols. But man, once you do, it's a lot quicker to draw this thing than it is to draw that thing. Right. This is, to the casual observer, this makes a whole lot more sense. But once we know what we're doing, this is way faster, way easier. Okay. Here's that circuit. And they say when the switch is closed, which means connected here, we have a place for current to flow. The current can flow. Okay. And when the switch is open, the current can't make that jump. Okay. And so we have what's called an open circuit, and current does not flow. Okay. Closed circuit, current flows. Open circuit, current does not. Now, finally, for the physicists in the house, you probably saw my mouse movement, and this arrow, it says current this way. Okay. So just a quick historical note, way back when electricity was first being discovered, I almost said invented, was first being discovered, and we were like rubbing fur on glass and noting charge and whatever. The expectation, the guess was that whatever was moving was positive, and it was moving from positive to negative. That's what everybody thought, was moving from positive to negative. Well, turns out we were wrong. Not me, I wasn't there. They were wrong. And it doesn't move from positive to negative. What's actually moving is the electron. The electron is the thing that's moving, and it moves from negative to positive. But at that point, once we had that understanding, it was too late. We had an entire industry built around the idea that the movement was from positive to negative. And so when we talk about it, we talk about how things are moving and how we trace things through a circuit, we trace them positive to negative. Does it make any practical difference for most design? No, not at all. When you get into the deep physics of it, that's when it starts to matter, is like, where are the electrons moving? What are they doing? And so to that end, they say we are going to use conventional current as we talk through this class. Again, it doesn't really matter. It's just, sort of we don't want to blow anybody's mind when they get to physics and they go, wait, what? It's actually going the other way? Yeah, it's actually going the other way, but it's too late now. We're committed to conventional current. I heard years ago, the US Army was like, well, we're going to do this. We're going to do electron flow. And they spent like 3 or 4 years teaching everyone electron flow as they went through their classes. And it was just a nightmare and nothing. They're like, forget it. We're going back. So for the electronics design world, this is what we talk about. In the physics world, this is what we talk about. And that's where I'd stop with this PowerPoint. Okay. That's as far as I would go with my students here. Okay. Because what else is in this PowerPoint? We're at the slide 24 right now. We get into Ohm's law. We get into series parallel circuit configuration, Kirchhoff's voltage law, series circuits, blah, blah, blah. The math behind series, way too much. Kids are in no way ready for this just yet. So I don't know why this is in this PowerPoint, to be honest. And I've been evangelizing for years that does not need to be here, but whatever, it is. So put in your notes, stop at slide 24. That's as far as you need to go. Now, don't panic. Like, we are going to get to this stuff. Like, it is in other places in the curriculum. I don't know. I just don't know why it's also here. It shouldn't be. So, Louis. So stop at slide 24. That's a good spot to stop. We looked at current, we looked at voltage, we looked at resistance. Cool. We'll stop there. Okay. Any questions on any of those things? Take a sip of water. Okay. Groovy. Quick reminder while we're paused here. I do record all these meetings and I put them in a YouTube playlist. The YouTube playlist is at the beginning of our collaboration document. That's one of the 2 links I told you to make, 2 shortcuts. It's way up at the top. So if you're ever, I know that I go through this far too fast because we have too much to get through, but those videos are available to you, roughly after the class ends. I have to exit the meeting. It has to convert it and I upload it to YouTube. But within a few hours, it should be up on that playlist. So if you look right now, you should see orientation and block 1 are up on that playlist right now. So just a reminder. All right. So a note from last time. Caleb, maybe, I think, asked about the ammeter. So in the activity in 115, they ask you to measure voltage, and they also ask you to measure current. Now, when you measure current, and with this, I'm going to talk about this fancy meter here. I want to earn my sponsorship dollars here. This meter, the reason I like it so much. Okay, so when you measure current, you have to measure it differently than you measure voltage. So I got to throw together a quick circuit here because my computer crashed and I didn't save that circuit. Quick reminder to always save often. Boop. Boop. I'm just rebuilding that one from earlier, so don't panic. I'm like, wait, slow down. I can't cut. No, I'm not. You don't have to follow along with this. I'm just rebuilding it. Come on, buddy. All right. And this was a 470. And this was a 1.2K. And this was a 270, I believe, and this was 9 volts, I think. Okay, cool. So when we were measuring voltage, it was super easy. You would just take your multimeter and you would measure on either side of a resistor. Pow, pow. And there we go. But to measure current, you cannot do it that way. Okay. When you measure current, your meter acts like it's a wire. It acts like it has no resistance whatsoever. When it's a voltmeter, it acts like it has a ludicrously large amount of resistance. It acts like acts like a giga ohm resistor, which is a billion ohm resistor. That's what it acts like when it's a voltmeter. When it's an ammeter, though, it acts like a 0 ohm resistor. And one thing we're going to learn about in tomorrow's block is that if I put a 0 ohm resistor here, it's just going to bypass this resistor. It's going to be like, forget that. I'm not going through all this work. I'm just going to take this quick little shortcut over here. Now over here, this is a billion ohm resistor. It's not going to take that shortcut. Forget it. That sounds like a hassle. I'm not going up there. So I'm going to take this path instead. So it works for voltmeters, but it does not work for ammeters. Here's what'll happen if you do this in real life. You set your meter to amps and you go ahead and you put it on either side of the resistor and you will get a reading of 0. And you'll be like, that's weird. And what you didn't know is that you just broke your multimeter. Okay. What will happen is your current will spike because there's no resistance and you will blow the fuse in your multimeter. Now, most multimeters don't tell you that in they don't like, error, you blew the fuse, right? They don't tell you that. It just reads 0 on current. And you're like, oh, I guess there's no current. No, you just blew the fuse. Okay. Now, as those of you with teaching experience can imagine, if this will happen with students constantly. Okay. And it's not necessarily fair to give them a hard time about it because they're learning, right? But man, that's going to happen all the freaking time. You're going to be constantly, and again, the fuses are $1, so it's not the end of the world. To me, it was the time, like, oh, all right, Zach, bring me your meter. Okay, I'll unscrew it, take it out, take the 9-volt battery out, put a new fuse in, put 9-volt, here you go, use it again. Oh, you blew the fuse again? Great. Okay, bring it back. Like that kind of thing was a hassle. So this meter, I'm gonna stop sharing for a second so I can be bigger. All right. So this meter right here. Okay. If you want to write down the model number, you can. It's MS8268. Someone wants to throw that in chat or on the collaboration document. MS8268. This meter is cool for a bunch of reasons, but none of them matter as much as this down here. Focus, you jerk. It says resettable. Okay. In your house, you have circuit breakers. So if you make a bad and you blow a fuse, quote unquote, you can walk down to your panel and you can click a circuit breaker. I'm presuming if you have a somewhat modern circuit panel, because we don't have to replace fuses. They did the same thing in here. They have a thermally resettable fuse. And so if a kid makes a mistake and they blow the fuse, you just turn this off, wait 5-10 seconds, turn it back on, good to go. No, you don't have to replace any fuses. Oh, so awesome. So awesome. While I'm talking about it as another teaching tool. So when I go to, I'm going to measure voltage, cool, it's ready to go. But the kid's going to go measure current. So they're going to switch it to current, right? They're going to switch over here to like milliamp range. Watch what happens. And listen. Can you guys hear that? Can't hear that? Look at the other side. No? Weird. Thanks, Zoom, for... Anyway, it's beeping. It's going beep, 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 beep. So it's beeping. It's also, if you take a look at, it's flashing. Okay. And I can hear that beeping from basically across the classroom. I'm like, wait a minute, what are you doing? What are you doing? Why is it beeping? Right. That means they're trying to measure something, but these leads are in the wrong spot. Right. Now, if I pull this lead out, it stops beeping. This stops flashing, but it's still lit up red, reminding me, hey, buddy, that's where you got to plug the lead. You got to plug it in right there. Oh, okay. So let me take my lead and I'll plug it in over here. I used to have this problem a lot where it looks like it's plugged in, but the kid didn't push it in all the way, right? But if I look at, I can still see the lights on. The lights on, that means it didn't plug it in all the way. When you plug it in, that light turns off. So it's helped me troubleshoot multimeter issues way faster because I can a 2-second look at the meter and I can tell if it's set up right, or I can hear it, right? But if I want to go back and measure voltage, up, beep, 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 beep. I got to move that lead back over to this side. So for me, like, especially those two features, worth the cost of admission, right? They're worth the $40, whatever this meter costs. It's pretty awesome. It has a light in case you're doing, electronics at night. So pretty neat. The meter you guys have, you're going to be breadboarding later today. Where's that meter? Meter, where are you? Anyway, the meter that you guys have, just a warning, it has a hold button in the top left corner, which will hold your value. And every training, somebody accidentally hits that hold button, and then they spend 2 hours trying to figure out why their meter doesn't work. So keep an eye on that. There's a hold button that locks in whatever value is on it at that moment. Watch out for that. You want to make sure that you don't have that hold button pressed down. Otherwise, you'd be very confused. Okay. Cool. All right. Time for 114. Okay, so kind of in order, right? 111 was the safety quiz. 112 was the discovery activity and the breakdown I just gave you after that. 113 was scientific engineering notation, which you guys did in the block. And now we're at 114. So we're kind of on track here. Okay. 114 is another discovery activity. I thought your meter was broken. Yep. Yep. Okay, so 114 is another discovery activity. Okay, we're just looking at analog components and seeing what they do and what they are and whatever, but we are giving a little background as we go. Okay, and so there's a nice little presentation. You would give this before you do the activity. Okay, and the big takeaway from this presentation is, oh, I already had a PowerPoint open. Is how do we figure out the value of resistors and capacitors by just looking at them? That's what this whole PowerPoint's about. Okay. Okay. So here's a resistor. All right. You guys saw them in your bags that you got. You've seen the schematic symbol a little bit, but these are resistors. Okay. They're measured in ohms, named for Georg Simon Ohm. But who cares? And also we have an Ohm's law, also named for the same person. Okay. We use the symbol omega, Greek symbol omega, to use for ohms. I don't know why that decision was made, because it was well before I was born. But to me, if we used an O, that would be really confusing whether or not it was like a 0, right? If I said like 100 was like 120, was that ohms? I don't, that's why I like omega and don't have as much confusion there. Okay. Some pictures of some different styles. This is like, they call this the dog bone style because it's like a little bit narrower in the middle. This is a more older cylindrical style. They have variable resistors and little itty bitty tiny, they call them surface mount resistors. These are very, very, very small. There's some comparisons so you can see their size. Okay. Now, common misconception kids have is that the physical size of the resistor tells you how much resistance it will have. Not true at all. The This one down here could be a 10 mega ohm resistor, and this one could be a 2 ohm resistor, or vice versa. The physical size tells you nothing about the amount of resistance. Okay. Common misconception people have. So we have to look at it to figure out its value. Now, resistors are very old components, and the way it was done was decided well before you could clearly print numbers on these things. So they use these stripy color codes. Okay. So we have these stripes of color, and they tell us the value of the resistor. Okay. So this is how this works. All right. There are effectively 3 bands we care about. Now, there are 4-band resistors, 5-band resistors, etc., but these 3 are the main takeaway. Okay. So the first 2 bands, the first 2 colors are the first 2 numbers. So I look at, my first band and I follow it down my chart. And again, you don't need kids to memorize this chart. It's in the engineering formula sheet. It's a Google away. So don't get too burnt out on kids memorizing this or anything. Okay. So they take this color, they follow it down, they find it in the chart. So I read this as orange. I would roll that down and say, okay, so that's a 3. And then the next color is white, and that's a 9. So 3, 9, those are the first 2 numbers of this resistor value, whatever it is. We know it starts with 39. Okay. Now, the third band, they call it the multiplier. I teach this slightly differently than you see here. Here's the language I use. Use your teacher language. Okay. I say, how many more zeros do we add? How many more zeros do I add? So here's green. So that means I would add 5 zeros. So 3, 9 followed by 5 zeros. That's your number. Okay. They have a multiplier in here, 100K, but I find that kids don't really know what to do with this number. You know what I mean? Like, do they put the 3, 9 in front of it? Did they multiply it in their calculator? Like, kids generally find this a little confusing. So the how many more zeros do I add tends to land a little bit better in my experience. So 3, 9, and then 5 zeros. 3, 9, and 5 zeros.
Mike, I have a question.
Yeah, Greg.
How would you say that if you didn't use your way, if you did the 100K, how would you?
Good question. So let me write down mine. So there'd be 3, 9, and then 5 zeros. 1, 2, 3, 4, 5 ohms. Okay. So what they're suggesting is you would take 3, 9, and then multiply it by this number. So you take 3, 9 and multiplied by 100K. So 100K is 100,000, right? So that's 100K. So they're saying that times 39. So you put like 39.
Perfect.
So that number and this number should be the same.
Thanks.
No problem. And again, maybe some kids will take this way better, my way better. Who knows? The other benefit to my way, if I can toot my horn for 1 second, is that we really then only need this information, right? You really just need 1 column because it's the same information, right? These 2 columns are the same. And if I say how many more zeros, I'm in the same column, right? So I only ever do that. When I was in college and, you had to memorize the color code. So, I know the color code. I have mnemonics for the color code. So that's where that is. Now, if a kid turned this in, is this the right answer? No, I'd mark it wrong. Why would I mark it wrong? I'll give you a hint. It's numerically correct.
It's not engineering notation.
That's not engineering notation. Correct. And this is still in the crashes being a jerk grading about engineering notation thing. So this is far too many zeros. So, okay. So let me move it back. I can go 1, 2, 3. Okay. And then that's probably still not enough. So I'm going to go more. 1, 2, 3. Okay. So I moved it back 6 places. So it's 3.9 times 10 to the 6th. Sorry, that 6 got a little away from me there. 3.9 times 10 to the 6. And if I were to look at my metric prefix chart, that would be mega. So that would be 3.9 mega ohm. That would be thumbs up right answer. Now, to nip this in the bud ahead of time, what if I have students that are colorblind? What if I'm colorblind? Sure. That is an issue. I will tell you that Project Lead the Way takes pretty great pains to make sure that they never, in activities on the end of course assessment, if they ever have a color, they write underneath what it is. They say, this is brown, this is orange, this is green. The biggest issue you're going to have in your classroom is, hey, I've got my bag of resistors here. I can't read them. And in that case, you just tell the kid, hey, grab a meter, throw your leads on it, and it is what it is. Okay. All right. So they take us through some practice here. So this is brown, black, red. Brown, black, red. Get out. Brown, black, red. So I would say brown is 1, black is 0. And then remember my language. I say, how many more zeros do I add? How many more zeros do I add? Okay, so red is 2. So I'm going to add 2 more zeros. So this would be 1 for brown, 0 for black, and then I add 2 more zeros. And this is a great problem because it almost immediately shows if kids understand this multiplier or not. Because if they don't, they're going to say, oh, there you go. Red's 2s, 2 zeros, done. Red's 100, there's my 100, done. Nope, wrong. Right? This should be 1,000 ohms. Of course, I wouldn't let that slide because that's not engineering notation. Move my decimal place 1, 2, 3 times. That should be 1 k ohm. Now, I haven't talked about this 4th band yet. Okay, this 4th band all the way over here is your tolerance band. So resistors are made incredibly cheaply. Holy cow, so cheap. And most of the time, we don't need them to be spot on a particular value. It's okay if they're off a little bit, high or low. It doesn't really make that much of a difference in almost every application. So when you buy a 1 k ohm resistor, there's a good chance it's not 1,000 ohms exactly. It's definitely not 1,000.0000 whatever, right? So the tolerance tells us what it's allowed to be. So when that band is gold, which is very common, that means you have a 5% tolerance. That resistor is allowed from the factory to be 5% below 1,000 or 5% above 1,000. So what's 5% of 1,000? 50. So it can be 50 below. So it could be 950 ohms up to 1,050 ohms. That's like what would be okay. All right. So that's what that tolerance means. If you see a silver, that means it's 10% tolerance. Or if you have a resistor that doesn't even have a 4th band, that means 20% tolerance. That's pretty cheap. You don't see that very often. Okay. Here's another one. This is actually the one we did already. This is the first one. It was orange, white, green. So 3, 9, and 5 more zeros. 3, 9, 5 more zeros gives me 3.9 mega ohm. Now, these are good. This is a thing that just skill that you're going to have to do because you're going to have them on your desk and you got to figure out which one's which and all that good stuff. But this problem is actually far more practical. So, all right, what do we need for our circuit here? Okay, we need a 1.5 k ohm resistor. Okay, which one's that? Right? So going this way from number to color is a more practical skill. Okay, so this 1.5 k ohm means it's actually 1,500, right? That's what we're looking for. Okay, so the first 2 numbers are our first two colors. So 1 is brown. It's always a fun moment when kids try and abbreviate and they're like B. I'm like, is that brown? Is it black? Is it blue? What does B mean? Oh, okay. I'll do BR. Okay, fine. BR. Okay. So BR brown. All right. And then 5, let's see, that's green, right? So G. Oh, wait, is that green? Is it gray? Is it gold? What is that? Oh, okay. Oh, I got gray. I'll do GR. Well, that's still not good enough. Green. Is it green? Is it gray? All right. I got to write it out. Oh, Crash, you're killing me. All right. So brown, green. All right. And then how many more zeros? 2 more zeros I'm going to add. So that would be red. Okay. And they said they want 5% tolerance. So again, that's my gold. So I'd do gold as my last color. The tolerance honestly is not all that relevant. I don't think it's not all that practical and important to what they do in this class. If I'm putting astronauts in space, yes, that's very, very, very important. But for our purposes, not really that critical. Okay. All right. So the other thing we have to talk about here are capacitors. So capacitors are cool because capacitors store up charge, and it takes time for them to do that. One of the good and bad things about electricity is it happens immediately for the most part. Like on all time scales that we are concerned with, it happens now. But that can be a problem when we want to build circuits that time passes, right? That things happen over time. They don't happen immediately. For that, we use capacitors because capacitors take time to charge. They take time to discharge. Okay. They're a little bit like a battery in that they charge and discharge, but there's no chemical reactions going on inside. It's all electrical. You have a big old plate on one side and a big old plate on the other, and you separate charge across those two plates. Your electrons can travel across, your protons do not. And so you get this big separation of charge. And so it stores up this big potential. It's like stretching a rubber band, right? You have this huge potential stored up. And then when you let those electrons and protons come back together, poof, you get this huge discharge of voltage. Okay. So that's great. There's the schematic symbol for it. There's the physical component. There are a couple of different styles. You know what? Let's, I'm just looking at 202 right now, and I got a couple more slides to get through. Let's go ahead and take a quick break. Let's take a 5-minute break. 207, we'll come back and we'll finish up these slides. Zoom recording. Okay. So before the break, I said that capacitors were these plates that separate charge and basically store up. Now, if you remember when I talked about resistors, I said that the physical size tells you nothing about their resistance, and that's true. Capacitors aren't exactly the same, though. Capacitors, part of their capacitance has to do with the size of these plates. The more surface area of these plates, the more capacitance. And so generally speaking, a smaller resistor probably is less capacitance. Probably. They have all these tips and tricks and ways that they've like squeezed capacitance into small packages. But for the most part, like if you see these disc capacitors, those are going to be pretty small capacitances. Okay. These units are pretty weird. Capacitors are measured in farads. And like 1 farad is a really large amount of capacitance. It's for most applications way too much. A 1 farad capacitor is about the size of a liter bottle. It's huge. People in like car audio sometimes will, like big car stereos with huge subs, they'll put in like 1 farad capacitors that soak up charge. So when you get a big bass hit in your music, the friggin' lights in your car don't dim. Your headlights don't dim if you have these big capacitors in there. So the point of that story, though, is that our capacitances then are really, really small. So these disc capacitors are very, very small. Okay. And these modular ones are similar. Down here, we have electrolytic capacitors, two different kinds. Now, one thing I want to draw your attention to is how the schematic symbols are different. Okay. In the top ones, how can you tell which is the positive and which is the negative? You can't, because there isn't one. Okay. On these type of capacitors, there's no polarity. Doesn't matter which way they go. Okay. But as engineers got better at designing these capacitors, they found ways of making the plates work better for positive and work better for negative. So in these electrolytic, there is a positive plate and a negative plate. So these, they do have polarity. These, it is important which way you put them in. Okay. And if you put in an LED in backwards, it just doesn't work. If you put in a capacitor in backwards, you might get fairly exciting results. Inside these capacitors, kind of, you saw it maybe from the name here, electrolytic. They're like rolled up like a ho-ho. They're like rolled up plates. Okay. Like roll them up in a spiral. And then there's an electrolyte, there's a liquid inside. And if you do bad things to these capacitors, you overvolt them, you put them in backwards, etc., you're going to usually get a big current spike, and you're going to heat up this fluid inside. And for my POE folks out there, what happens when you heat up a fluid in a confined volume?
Blows up.
Expands.
Yeah, both of you are right. It expands. And eventually, that pressure will increase so much that you will rupture the vessel that it's in. Okay, and these are famous for that. Back in the ye olden days, you know, these things would fail. You'd look at a circuit board and you'd see this big like mound of grossness as these would explode. Really exciting. Is a good story for your kids. When they would fail, the bottom part here where the leads connect were typically the weakest part of the capacitor. And so that's what would fail. And so you have this pressurized liquid that wants to get out, and it's going to get out down. And every action has an equal and opposite reaction. And so if you're forcing all this liquid out down, what do you think happens to the body of the capacitor? It goes up. And so we were having little capacitor rockets that would come shooting out of devices when they would fail. And so like, if you look at like old safety videos and stuff, they'll be like, don't lean over a circuit board when you're working on it, because these capacitors can come shooting out at you. In more modern capacitors, they perforate the top. There's like a little X in the top of the capacitor, and they perforate it. So if it fails on the top of the capacitor, not the bottom. And so it makes a mess, but it doesn't come rocketing off the board or anything. So anyway, that's a little safety thing. You might see those pop in your classroom. Again, we're not dealing with such large capacitors. That's a big danger, but just something to watch out for. And there's some little ones too. Okay. So how do I read the value on a capacitor? Electrolytics are easy because it's just printed right on there. Thank you. Nice. So this just says 10U. Cool. 10 microfarad. Thanks. Got it. Awesome. Okay. This one says 0.47 mu-f microfarad. Great. Cool. Thanks for letting me know. So those are a lot easier. The disc capacitors are not easy. I mean, they're not too difficult, but just to give you a quick context on this, many years ago, I was on the team that took the final for this course and figured out where the differentiations lie for basic, proficient, whatever they call it now, distinguished. We kind of like laid down the lines for like, this is where you need to be. And part of that, it was a really cool experience. And part of it, they gave us every single question on the final and they ordered it from easiest to hardest based on tens of thousands of kids who have taken this test. How many got each question right? Here's the easiest question all the way to the hardest question. The reason I tell you this is because the hardest question on the end of course assessment was this right here. This question right here was the hardest. The question kids got wrong the most. Why? Probably because we do it now and then basically never touch it again. But just to throw it out to you, I thought that was kind of interesting. So you see this little disc capacitor and it says 472K. And so your kids are going to look at that and they're going to say, all right, that's 472K, 472,000, right? Because that's what K means. That's what we thought, right? 472,000 farad. Now, I make a big deal with my kids. I'm like, I told you two things. Number one, I told you that a farad is a very large amount of capacitance. It's like a liter bottle. So if 1 farad is a liter bottle, what do you imagine 472,000 farads would look like, right? It's got to be like a warehouse. There's no way that this little disc capacitor, the size of a Tic Tac here, is 472,000 farads. So that can't be right. That's not right. And okay. So we gotta deal with that. That can't be right. So the way we do these disc capacitors is kind of like the resistor. Okay. What we do is the first two numbers are the first two numbers. 4, 7. Done. Okay. The third number, how many more zeros do I add? Just like for resistors, right? That's part of the reason why I use that same language, because it translates here nicely. So 2 more zeros, 0, 0. Okay. Now, that still doesn't make sense. 4,700 farads, again, would be giant. So here's the last piece to remember. On a disc capacitor, whatever value they give you is not in farads. It is always in picofarads. Picofarad. Always in a disc capacitor. So whatever value they give you, it's in picofarads. Now that's obnoxious because that means we probably have to convert it, right? Picofarads. Okay, so if I want to figure out farads, oh man, pico, let's see, pico is times 10 to the negative 12. Yikes. So I have to go all the way back and make that work. And that's kind of obnoxious. But that's where that comes in. Now, I still wouldn't accept this as a correct answer. It's still not perfectly in engineering notation because I have 4 numbers over here. So I should probably move this back 1, 2, 3. Okay. So it'd be 4.7. Now this was times 10 to the negative 12. But I moved it back 3 places. So now I'm at times 10 to the negative 9. And that would be nano, I believe. So as you can see, like there's a lot of places to get that question wrong, right? There's a lot of places to get that wrong. The good news is we don't have to do much of it in the curriculum. Sort of here as a interesting note, as a thing, but we don't run into it all that often. Great question.
Thank you. Where did you get nano from? How did you know that negative? I understand the 12. You went to 9 because you did 3. Where did that come from again? I'm sorry.
If that's just the metric prefix for -9. I don't have a chart up here in front of me, but yeah, that's what the mnemonic for those who want, if you want a little mnemonic, the garbage men killed, that's above 0. The garbage men killed my mom's new poodle. The garbage men killed my mom's new poodle. That's my mnemonic. So that's tera, giga, mega, kilo. Those are the aboves, right? So that's times 10 to the 3, times 10 to the 6, times 10 to the 9, times 10 to the 12. And then below, smaller than 1 here, this is milli. This is micro, nano, pico. So -3, -6, -9, -12. You can call the poodle Fluffy if you want to go one more down. -15 is femto. We don't mess with that in this class.
Thank you.
No problem. The only thing I haven't mentioned here is this K. what's this K about? Well, that's how they do tolerance, like that fourth band, that gold band and resistors. They put a letter on it because they were like, what could be the most confusing way? I know, let's use a letter. So they put a letter on here, and it corresponds with this nasty looking chart over here. So you'd say, oh, okay, so it's got a K on it, so it's plus or minus 10%. Please note, kids should memorize none of this. Like, they should never memorize this chart. What a waste of time. It's on the engineering formula sheet. It's Googleable. That would not be a good use of anybody's time to memorize that. I just need to know how to look at a disc capacitor and pull the value off of it. Okay. Any questions on that? I think that's the last slide here. Oh yeah, there they go. I don't like this. More commonly expressed as 0.0047 microfarad. Not in my house. I wouldn't express it as that. I would use nanofarad. I don't want the 0.00 business. Get out of here. No way. So here they give you a little example. So I'm going to give you like 2 minutes on your own. See if you can figure out what this is. No pressure. I'm not going to ask you to answer. But see, just take a moment on your own. See if you can figure out what that would be. This is a great tactic to take when you're teaching, because there's a real cognitive difference. Sorry, I was far away from my microphone. It's a real cognitive difference between following along the teacher doing something and actually doing it yourself. And you'll find that there's a lot of kids will be like, yeah, I'm with you. I got you. I got you. I got it. I got it. And then you ask them to do it and they're like, oh, I don't got it. Right. So even something small like that, just spend 2 minutes working on your own. You can walk your classroom. Hey, you make sure you're working on this. Let's see if you've got it. Okay. Sometimes, depending on the class, they will do it honor system. Sometimes you'll have to ask them to write it down somewhere. You don't have to turn this in, but you got to write it down on something. And so you make sure they write it down. Depending on the class, we're an iPad 1-to-1 school. So every kid has an iPad. So depending on how confident they are on a topic, I'll have them write their answer down on the iPad and then 3, 2, 1, everybody hold it up at the same time. 3, 2, 1, up. And then I can really quickly look around the room and be like, oh, we don't get this. Like 2/3 of the kids have the wrong answers. Okay. All right. Put them down. I know I need to spend some more time on this. Or most of us got it. Okay. It's a quick temperature check on the room. What you want to stay away from, and I'm as guilty of this as any teacher on the planet, is going, what's the answer? And one kid quickly goes, here's the answer. I'm like, all right, cool. The class has got it. Right. Remember that the kids that don't get it are the quiet ones, right? The ones that don't say anything. And those of you who've been teaching for a while, you know what I'm saying. It's so easy as a teacher to pat yourself on the back because 2 or 3 of the kids got it. And they're like, yeah, here it is. I got it. Yeah. But that's not what we're searching for. Right. So this one here, the first 2 numbers are the first 2 numbers. So 3, oops, where's my pen? Oh, no. Oh, no. Friggin' PowerPoint. All right. Pen. There we go. First 2 numbers are the first 2 numbers. How many more zeros do I add? All right. I'm seeing people miming to me in the video. I love it. So 1 more 0. Okay. So 330. 330 farads. Done? No?
Picofarads.
Yeah. Pico. picofarads. Picofarad. Okay. Is that in proper engineering notation? Yeah. Yeah. There's only 3 digits here. That's fine. That's in proper engineering notation. So we can leave that alone. 330 picofarads. And then they said J, my tolerance. So here's J. Okay. So plus or minus 5%. Questions? Okay. Here we go. Okay. I don't know why this one immediately gives us the answer. That's not very useful. Thanks. 103K. So 1, 0, and 3 more zeros. 1, 0, and 3 more zeros in picofarads. I do not like this answer. How dare you? 0.01 microfarad. I would have net 10 nanofarads. That's what I would have said. 10 nanofarads. Why? Because I would move this decimal place back 1, 2, 3 times. Be 10. And I'd be moving from pico up to nano. What they did is they went another 3. 1, 2, 3. And gave us 0.1 microfarad. No thanks. Okay. Some other quick little components, 7-segment display. We're going to deal with those in class. LEDs you've seen, just some other things to look at. Fuse you might see in the multimeters. We're not going to mess with the diode. We're not going to mess with the voltage regulator. None of those are in the course, so don't worry about those. And that is 114. Discard. Okay. In the activity, your kids are going to practice, as are you, going to practice going from color code to value and value to color code. And then the activity portion of this, your kids are going to take 10 resistors from your classroom, and they are going to, let me actually pull this up. So I'm talking about it while it's up. Here we go. So here's just the practice, right? Here's some color codes, and they are written here. So don't worry about if you can see the color or not. So color code, then put a value, color code, value, right? All right. Now in your classroom, 10 random resistors from your instructor, and then they fill out this chart. Here's the colors for resistor 1. Here's what it should be. Here's with the tolerance, how low it should be. So let me give you a quick example that we did before. So brown, black, red, gold. That would be a 1 K ohm resistor. And it has a 5% tolerance. So that means the minimum accepted value it could be would be 5% below. So it'd be 950 ohms or 1.05 K ohms. Okay. So that they would figure out just from looking at the resistor. Then they'd measure it, put the multimeter on there and see. And if I get like, let's say 1020, then I would say, yes, it does meet the tolerance because it's within those two values. If I measure it and it's 1150, I would say, no, it does not meet tolerance. As an instructor, this is a wonderful way as you're walking around your room. If you see a kid and they're like, no, 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 something's wrong. It's not unheard of to have resistors that are out of tolerance in your classroom, but you certainly shouldn't have like 10 of them, right? These should basically all be yeses. And if they're not, something's going on. Okay. Now, while we're on this subject, you guys have to modify this a little bit for yourself, because I'm guessing you all don't have 10 random resistors floating around your desk. Maybe some of you, I don't know. I saw some cool, maybe Zachary's got some 10 random resistors floating around his desk, but you probably don't have that. Okay, so options for you. Okay. You can use the resistors that were in your pack. They are all the same colors. So there'll be 5 of these that'll all be the exact same colors, but you can measure them and the measurements should be different, at least marginally. That's an option. Also, another option for you when you complete this is in our course, in the core training in block 2. Here we go. There is this video. Again, handsome guy, great voice. Working on this video here. And personally, I'm a little proud of the production value here because I got the meter here. And then anyway. I did 5 of them here, different colors, and then you can see the readings on the multimeter. So you can use those if you'd prefer. Option 3, which is my least favorite option, is you can do it in Tinkercad if you want, but because it's a simulation that they'll all be spot on. There's not going to be any tolerance there. If it's a 1K resistor, it's going to be 1,000 ohms exactly. So if you want to do it that way, you can, but that's my least favorite option. Okay. So that's 114. Remember to keep an eye on like what steps it asks you to do. You're not doing all of the activity, right? You're just doing some of the steps. Okay. Cool. 2 last things here. I'm going to go slightly out of order. I'm going to talk about 1, 2, 3 first, and then come back to this breadboarding thing. So, I'm going to share my iPad here. Stand by. Oh. Where did it go? Sorry. Try this again. There we go. All right. Can you guys see my engineering notebook? Yeah, awesome. Wonderful. Okay, so 1, 2, 3. I know you're like 1, 2, 3. What the heck? Huge jump. I know. I remember I said it's going to be a little out of order here in the beginning. But 1, 2, 3 is about the binary number system. Okay, we have to represent the world with 0s and 1s. And one of the ways we're going to do that is with a number system that only uses 0s and 1s. Oftentimes in this curriculum, we're going to compare decimal to like get our feet grounded because the kids are all familiar with decimal. And then we'll talk about how that relates to binary. Okay, so the decimal system. Okay, we start with 0. Okay, and in the decimal system, we have 10 unique characters that represent numbers. So we have 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. Now, counting 0, that's 10 unique characters, right? 10 things. Okay, now I'm out. I've run out of numbers here. So what do I do after 9? Give me an audible response here. What do I do after 9? Where do I go?
My audible response is it's my screen sharing is still nothing showing. So sorry.
Are you the only one? Can anybody else see my thing? No,
I can see it. Add 2 numbers together. Put 2 numbers next to each other.
All right.
Is it A through H?
Not just yet. We're still in decimal.
Oh,
We're still
yeah.
in decimal.
What
Yeah,
is
yeah.
it?
So, so decimal,
uh,
I'm just going to go 10, right? Now I use the word carry a place. All right. We carry a place here. All right. So 0 through 9, and then we carry a place. When we've run on numbers, we carry a place, right? And we do the same thing. We do like 11, 12, 13, 14, 15, 16, 17, 18, 19. And then we carry a place, right? All the way up to 99. And then we'd carry a place up to 100. So that's what happens in decimal. We have 10 unique numbers and we run out, we carry a place. That's what we do in decimal. Okay. So then in binary, in binary, binary, B-I-N-A-R-Y. I don't know why when I start talking quickly, I don't know if it's I draw, I thought binary. I always add an extra syllable in there. It's not binary, it's just binary. So with binary, we have 0, cool, so far so good. And then we have 1, and now we're out. Binary only has 2 numbers. We have 0 and 1. Makes sense why we built the digital system using kind of binary here, because that's what we have in digital, right? 0 and 1. So what do? Well, I carry a place. Same thing I did in decimal. So I have 0, 1, and then what I would call 1, 0. Got to kind of get yourself out of the habit of calling that 10 when we're in binary, because that can lead to kind of a source of confusion, right? Especially like if we get big numbers that are like that. You don't want to have to be like, is that 1,100,000? No, that's 1101,011,01, right? That's how we would talk about that. So in binary, I've got 0, 1, then I carry a place, 1, 0. Well, then I can do 1, 1. That's cool. All right, 1, 1. Great. Now I'm out again. I'm already out of numbers again. So I got to carry a place. So now 1, 0, 0. You know what? Hold on. I got a little fast and loose on my grid lines here. Let me fix this. All right. So 0, 1, 1, 0, 1, 1. There we go. All right. So down here would be 1, 0, 0. And one of the things you'll probably notice is that binary numbers, numerically don't get larger, but like physically writing them out, they get large pretty quick, right? So this would be 1, 0, 1, and then 1, 1, 0, and then 1, 1, 1, and I'm out again. I've used all the combinations, and then I have to carry a place 1, 0, 0, 0. But what you're seeing the basics of right now, which is kind of, mind blowing, is that we can represent anything we want using 1s and 0s. It just, takes a bunch of time. Right? We can just copy it down as we go. I missed one here. 1, 0, 0, 1. So that's the binary system, okay? That we only use 0s and 1s, and we use it to express any number we want. Now, this little chart is handy and nice and wonderful, but it certainly loses its practicality if I say, hey, can you convert 738 in decimal to binary, right? Then I don't want to make a chart that's 738 rows long. No thanks. Okay. So we have a couple of systems in place to do some conversions here to make our lives easier. So we don't have to do this chart thing. Okay. Now, again, from like how much do we care if kids get this thing? There's no shortage of binary converters. The calculators can do it. The Windows calculator can do it. You can Google it, etc. But definitely like 0 to 16, kids should be able to like pull that from, a quick calculation, whatever. They should not have to go to the computer for the calculator for 0 to 15. Throughout this course. But for converting, okay, they have 2 methods that they talk about in the curriculum. Okay, the first one is called successive division, if you want to be a nerd about it. successive division. And some people like this, some people don't. Let's pick a number. Let's pick 731. I don't know, just making it up. So here's what you do for successive division. You write your number down, 731. And then you're going to divide this number by the base that you want to convert to. What the heck is a base, Crash? Okay, so the base is like the number system. So binary is base 2. That's base 2, binary. There's other ones. Ternary is base 3. Octal is base 8. Hexadecimal is base 16. There are definitely other number systems out there, but right now we're focused on binary, which is base 2. So 731, I'm going to divide by the base. I'm going to divide by 2. Okay. Now, one thing I like to model with my kids is breaking out the calculator. I think calculating stuff in your head has a place, but I think if you model it for kids, then you expect them to do that, and then they're going to make mistakes, right? And there's kind of a shame for reaching for the calculator. Remember when you were telling everybody 20 years ago, you won't always have a calculator in your pocket? Well, surprise, they do. So nothing wrong with reaching for the old calculator here, right? And so 731 divided by 2 is 365. But here's the weird thing, all right? So we're going to write 365. But instead of saying 0.5, we're going to say remainder 1. And you're like, remainder? I haven't heard about a remainder since 3rd grade or something. But that's what we're going to do. We're going to write down 365 remainder 1. Okay. And then we're going to take 365 and we're going to divide it by the base. Okay. 365 divided by the base is 182 remainder 1. And we're going to divide that by the base, 182 divided by 2. This is the successive division part of it, right? We're successively dividing. So that was 91, but you'll notice there's no 0.5 here, right? So remainder 0. (91) divided by 2 is 45. Remainder 1. 45 divided by 2 is 22. Remainder 1. As I get lower and lower, kids get more excited about giving me the answer. Oh, I didn't know that one. 20. I didn't know that one. 22 divided by 2. I can do that one. 22 divided by 2. Okay. 22 divided by 2. Oh, that's 11. Remainder 0. And 11 divided by 2 is 5. Remainder 1. And 5 divided by 2. Whoops. 5 divided by 2 is 2. Remainder 1. This is interesting. What's 2 divided by 2? It's always a good spot to test our algebra skills here, our mathematics skills. All right, 2 divided by 2 is 1. Remainder 0. And what's 1 divided by 2? I love teaching this. I do this. We've just done this like 12 times.
Remainder 1.
And every time the kids go 0.5, I'm like, what did we just do? What did we just do 15 times here? No 0.5s, right? But it's a weird concept for them to understand. So 1 divided by 2 is 0. Remainder 1. And spoilers, every single conversion will end that way. So that's how you know you're done. Every single one, it will end that way without fail. This will be the end of every single problem. You'll end up with a 1. 1 divided by 2 is 0. Remainder 1. They will all end this way. Okay. Now what, Crash? You just wasted my time. We did this whole big thing. Okay, what? Now, I heard a teacher say, I love this. I stole it. Now the tree falls over. Kablam. Imagine this is a tree right here. and it falls over to the right. Kabloom. And this number here, so I'm copying this number from bottom to top. 101, 101, 101, 101, 101. That was a weird a weird pattern. I did not do that on purpose. 101, 101, 101, 1. This, friends, is 731. That's the conversion we just did by doing successive division, which is kind of mind-blowing. Okay. If we did a big old 732 line chart, we would end up with this answer. But that, annoying as it was a whole lot easier than doing 732 rows of a chart to convert. Okay. So that's how successive division works. So we're going to do one more little example here. We're going to do a shorter one, and I want you guys to try and do this on your own. So we're going to do a much shorter example here. We're going to do 48. Okay. Spend a couple minutes, 1 or 2 minutes on your own. See if you can figure out what 48 decimal is in binary. It's another little teacher strategy. Tell kids you want them to start it, give them 60 seconds to work on their own, and then kind of quietly start to work through it on your own on the board. And kids who are stuck early, you might unstick them a little bit so they can work on their own. So 48, I'm going to divide it by 2 to start with. 48 divided by 2 is 24, remainder 0. "24 divided by 2 is 12, remainder 0. And 12 divided by 2 is 6, remainder 0. 6 divided by 2 is 3, remainder 0. And 3 divided by 2 would be 1, remainder 1. And 1 divided by 2, 0, remainder 1. And then the tree falls over. So my answer is 1, 1, followed by 4 zeros. Okay. All right. So this method gets us from your decimal number to your binary. But we also need to be able to go the other way, binary to decimal. And for that, we have something called weighted multiplication. I thought I invented weighted multiplication. I did not when I found out it was already a thing. I used to call it the chart method. Weighted multiplication sounds way more fancy. So weighted multiplication, though, and I actually much prefer weighted multiplication to successive division. In fact, I use weighted multiplication both directions, decimal to binary, binary to decimal. If I have my way, I would just use this one method. Okay. So the way this works, you got to do a little work in the beginning here. Okay. So you got to build a little chart. And your chart is base to the 0, base to the 1, base to the 2, base to the 3, base to the 4, base to the 5, and so forth. Now, again, our base, we're dealing with binary here. So that means 2 to the 0, 2 to the 1, 2 to the 2, 2 to the 3, oops, 2 to the 4, 2 to the 5, etc. So a 2 to the 0, for those of you who don't know, 2 to the 0 is 0. Is it 2? What is it? Oh, it's 1. It's 1. 2 to the 0 is a 1. I asked a math teacher in my session once, I'm like, explain why the 2 to the 0 is a 1. And it gave a good explanation, but I don't remember it. So I guess it wasn't that good. So 2 to the 0 is a 1. 2 to the 1 is a 2. 2 to the 2 is a 4. 2 to the 3 is an 8. 2 to the 4 is a 16, and then a 32. I don't have time to do it right now because we only got about 10 minutes left in our session, but this is a really cool discussion to have with kids. Like, where have you seen this pattern before? Like, how much space do you have on your iPhone, right? Oh, I got the 32 gig version. What do you got? I got the 64 gig version. Oh, okay. And then, anybody who's like into retro video games, we talk about, oh, that's like the 8-bit era, right? The Nintendo was the 8-bit, and then the Super Nintendo was the 16-bit. And, how much RAM do you have in your computer? This one has 4 gig of RAM or whatever. Like, you see this pattern again and again and again in computing and electronics. And this is why. This is why, right? In fact, we call this pattern 2 to the n. And I always joke in this class, if I ever call on you and you like spaced out for a second and you were just thinking about like sunshine and butterflies, and all of a sudden I say your name and you panic. If you say 2 to the n, you have a pretty good chance of being right. Like, this pattern comes up all the time. So just answer 2 to the n and you'll probably be fine. All right. So, so here's what I do. I got this chart made. Okay. And then I put my binary number in this chart. So I would put, like, let's say 1 0 0 1 0, just as an example. Okay. So here's what you do. Take 16. I got one. I can put a 0 here if I want to. It doesn't matter. I have no 32s. I have a 16. So I bring the 16 down, and then a 2. 16 plus 2. This is 18. Because I have a 16 and a 2. That means this number is 18. The decimal version of this number is 18. Okay. It goes a lot faster, I think. Almost too fast. So a different example. Let's just do another example. How about 1 0 0 1 1 0? So there's a 1 here in the 32 spot. So I buy 132. No. There is 1 here. So I get a 4 and a 2 and nothing there. So 32 plus 4 plus 2, that would be what, 38? Does that sound right? $32 plus 4 plus 2.
What is that called again?
This is called a weighted multiplication. Weighted multiplication. Now, like I said, I probably would use this to go the other direction. So for example, if I was like, what is like 54 in binary, I would go, all right, so 54. All right, so I definitely want a 32. Okay. So let's see, 54, I'm gonna break out my calculator here. 54 minus 32. Okay, so I got like 22 left. So yeah, I want a 16. I want a 16, thanks. Minus 16. Okay, and now I'm at like 6 left over. I can't do an 8. That's too much. No. Oh, but I can do a 4 minus 4. And I can do a 2. And then I'm done. So 32 plus 16 plus 4 plus 2 would give me 54. So some people like to just use this weighted multiplication method in both directions, which is fine too. I did the number 18 and 54. And what the heck was this? 32 plus this is 38. And all three of those numbers are even numbers. What do you notice going on in my chart over here that's the same in all three examples? Look at this column right here. This column, if I look at these, is a 2, a 4, an 8, a 16. These are all even numbers, right? The only way for me to get an odd number is this column over here. This is the only odd number. So from a you perspective / a teacher perspective, this is a nice little cheat that if I look at a binary number and it ends in 0, that's an even number. So I've had kids be like, I'm working on 1, 2, 6, 7, 8, 0, this crazy huge decimal number, right? And it's blah, 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 whatever. It's like 1, 0, 1, 1, 0, 1, 0, 1. And they're like, this is that. I'm like, wrong. They're like, oh, how did you know that? It's incredible. It's like a human calculator. Nope. But this is an even number and your binary ends in 1. So I know that's wrong. I don't know what else is, if this is a 0, then I guess I'm taking your word for it because that's a 0 and this is an even number and okay, fine. But that's a nice thing. It's a nice quick way to check as you guys are running through. If you look at that last binary number, if it's a 0, it's an even number. If it's a 1, it's an odd number. Okay. All right. I only have a couple minutes left and I have one other thing I need to talk to you about. So you guys are going to be breadboarding in this. It's your turn. Okay. So you're putting together a breadboard. Here it is. You're putting together a breadboard. Okay. Couple things on breadboarding. When you make your wires on breadboards, we want them to be nice and short. Okay. You want them really close to the board. You want this kind of thing. See how that's really close to the board like that? That's what we want to go for. Big loopy guys, we don't like those. Okay. It's too easy to get under them and get them unplugged and they're on top of things. And no, we don't want that. We want tight, low, nice, close to the board. Look at this one over here. That little red one. That's awesome. Nice, tight, small, close to the board. Okay. I don't think on this one, we click on it. Let's go. Stop sharing. No, don't stop sharing. On this activity, what are you wiring? You're wiring a switch and 2 resistors. Yeah. And they really take you through it in the activity. So I'm going to show you that in just 1 second. But we've got our little switches. They have 3 pins on them. Okay. And you wire positive power to one of the outside pins, negative power to the other outside pin. And then my middle pin goes to my resistors. When you are cutting your wires and you're trimming them down, you don't want like a big, huge area of exposed metal. We don't want this. This is too much because when I plug it in the board, you'll see there could be like extra metal hanging out. I don't want that. This one's actually kind of okay because if I push it in, there shouldn't be too much metal. Okay. But occasionally you see people strip like way too much and then you get a bunch of this exposed metal sticking out. That's bad news because you're going to like accidentally touch it to other things. Things are going to cross. That's no good. Okay. So you want that nice and tight, low to the board where you can, and kind of run from there. Okay. Let me show you what this activity is. Now, just for the sake of clarification and confusion, what you are going to do, let me go to the, it's your turn. Oh, damn it. Wrong button. Sorry. So I'm in the, it's your turn for block 2. Here's the safety quiz. Okay, fine. Here's 114. We talked about how you're going to put together that chart. Okay. And then here's the breadboarding section. It wants you to do this circuit theory breadboarding activity. Listen to me carefully. This activity is nowhere in the student curriculum. This is not a student curriculum thing. It's modified so that you guys could do it on this training. This is the only place you'll find it, is right here. Okay. It says circuit theory breadboarding activity. I'm in the middle of it's your turn 2, step 4. So when I click on that, here's this circuit theory breadboarding activity. Then it's nice. They say, this is what we're going to build. We're going to build a switch and 2 resistors. And they take you through like piece by piece. Here's the wires you should make. Here's where you can put the switch. If you want to be so granular as to put your switch in row 15, because they did, you certainly can. You don't have to, but you can. Okay. And so they take you through exactly what you're going to wire, what it represents. The switch is that, right? And we take you through all the way through there. I like this. They have these like hints here. So you could try it on your own, but if you get stuck, you can open up these hints and kind of take a look at, they're like 3 levels of help. So there's like a little help, a little more help, basically the answer. So you can take that as much as you need, which is cool. Okay. And then when on the submission form, they ask you to give us a picture of the breadboard with reading. You get your multimeter there and you're taking a reading. Okay. Let me grab that language, make sure I am saying it the right way. Here we go. Top view of your circuit with the power supply on, the switch set to on, and the multimeter showing the voltage drop across the resistor. One more
Hey,
thing.
Mike,
Yes, Eugene.
for that breadboard, for that top view, have
Yeah.
you found an easy way of taking a picture, holding the multimeter and getting everything situated all in one go?
Not an easy way. No, no. Mostly, the best suggestions I've heard is, employing someone else to come in and take a picture, or kind of holding your meter leads kind of in one hand. So I got my meter leads, kind of holding my meter leads in one hand and kind of getting them on your resistor, and then setting the multimeter next to it. And then, with my right hand now, I'm taking a picture of my circuit. I will honor system you guys. If it's 2 pictures, that's okay. If you take a picture of your circuit and you take a picture of the reading separate, I don't care. It's fine. Last thing. It says you have a 330 ohm resistor and a 165 ohm resistor. And somebody in this group is going to look in their pouch and say, I don't have a 165 ohm resistor. It's true. You don't. But you can take the 2 330s and you can put them in parallel, basically wiring them they're each end together. And when you take 2 330s and put them together like that, you get 165. And we're going to go through tomorrow why that's a thing and how that works. But for the purposes of this, you can put those together. And if you're like, Crash, I don't know what you're talking about, in those hints, they show you exactly how to wire that up. Okay. I want to be respectful of your time. I'm about 4 minutes over. So I'm going to stop there. And I'm going to stop my recording.